Yeah, good morning, everyone. Thank you. So today, actually yesterday, we saw equivalences between the homotopy category of DGLAs and the homotopy category is as deformation functors. Also, homotopy category of L-infinity algebras. And so far, it seems like L-infinity morphisms, in particular L-infinity quasi-isomorphisms of DGLAs are a good idea. But it's maybe not completely clear yet why L-infinity algebras are also a good idea. So yeah, I want to give some motivation for that. And basically talk about two constructions where L-infinity algebras really come in handy. And one is minimal models. Of DGLAs. For L-infinity algebras. And the other one is a construction called higher derived brackets. Okay, and the first result is G L-infinity algebra or L-infinity 1 algebra, but I won't talk about signs, so if G is an L-infinity algebra, G is isomorphic, H plus C, where H is and that means that that L1 vanishes and C is linear and contractible. Linear means that all the higher brackets vanish. The variable 2 is 0, and contractible means that the homology be 0. And yeah, and we also have there exists infinity quasi-isomorphisms. We can include H into G and project down to H. And doing this, so followed by F is the identity of H. Okay, so in particular, this implies that the deformation functor of G is isomorphic to the deformation functor associated to H. Okay, so basically we can, yeah. Okay.
Can I ask for the shapes and the gradients here? This is L infinity or infinity 1?
Well, it's true for both.
It's L1s and L2, I think.
Well, both for L infinity and for L infinity 1, this is just the arity of the bracket.
Oh, okay.
So it's not about the signs. So, yeah.
Yeah, but just, okay, thank you.
So this is, if this is an L infinity algebra, then this will have degree 1. And if this is, and the brackets, the higher brackets will have degree 2 minus n in general for the arity. So the degree of this in the L infinity algebra setting Ln has degree 2 minus n, and in the L infinity 1 setting Ln has degree 1. Yes?
In what category is the direct sum? Is vector spaces?
As L infinity algebras.
Is it also the bracket also this vector?
Right.
Yeah.
Yeah. Exactly. And it's also, of course, direct sum on the underlying graded vector space, but also in terms of the brackets. So all the brackets.
I think it's more a product.
Okay.
I mean not as vector spaces, but as elements.
Yeah. Okay. And I like product then.
But then, does the statement on the right say anything that so there isn't a direct corollary of the stuff on the left?
No.
Okay.
No.
Yeah.
Yes. Right. Just to point out that you have an inclusion and a projection, and these are infinity quasi-isomorphisms. Yeah. Yeah, and so H is unique up to L infinity isomorphism. And it's called minimal model of G.
Is it canonically unique? The isomorphism between the H, is it canonically true?
No, so there can be many. Yeah, so that's actually, I mean, an important point that there can be many higher structures which are all minimal models, but they should also all be L infinity isomorphic. Yeah, so that's sort of the next definition. Well, so G is formal. If H is isomorphic to underlying graded vector space with no differential, the binary bracket, and no higher brackets. So sometimes you might construct a minimal model which naturally gets higher structures, and then proving that it's actually formal is an extra step. And yeah, another corollary from this decomposition is that if you have quasi-isomorphism of L-infinity algebras, right, have it on the board. If you have a L-infinity quasi-isomorphism, then the deformation factors are isomorphic. Okay. Now to get back to the example of associative algebras. And yeah, basically there we saw we had this usual DGLA. This is DGV algebra. Then you can look at the L-infinity algebra. Basically what you can do is Hochschild cochain complex is constructed as the dual of the bar resolution. And you might have an algebra which has another nice resolution which is smaller. Then you can use that instead. And then, yeah, what you have to do is to sort of construct higher brackets, and this you can do via the homotopy transfer theorem. And so basically, the right-hand side is very big, and the left-hand side is very big, and the right-hand side could be smaller if you choose a small resolution. And yeah, that's something we saw yesterday in Philip's talk. So if we take the polynomial ring, so this is the algebra, then and E dot is the resolution. Then one can construct higher structures on there, on the right-hand side. So turns out that the differential is actually 0, but you get infinitely many higher brackets through homotopy transfer. And since by construction this is L-infinity quasi-isomorphic to the original one, they describe the same deformation problem, or at least isomorphic deformation problems. and then you can use this to quantize polynomial Poisson structures. And the fact that this is isomorphic to the same thing with 0, just the binary bracket, and 0 higher brackets. This is the higher theorem, and this is Kontsevich formality. But one formulation. Yeah.
So we can take any projective resolution as a bimodal. And then the home sets, are these then bimodal morphisms?
Yeah, right.
And yeah, maybe because I don't know, the homotopy transfer, this only depends on the algebra then, or from the complex, or is it also extra information of the algebra itself?
You also need a homotopy. And once you have a homotopy, then you can apply this homotopy transfer theorem. Yeah.
So I'm still parsing the theorem below in my head.
Sorry?
Does it sort of say that to give the data of the DGLA is the same as give an affinity structure on the cohomology of the DGLA? Okay.
That's one way to think of it, yeah.
Yeah.
But so there might be different different L-infinity structures on the cohomology, but they're all isomorphic if they are quasi-isomorphic to the original one. So that's sort of this formality statement. That's what I was trying to say here. It's not clear that, like, if it's formal, it's not clear that if you try to construct an L-infinity quasi-isomorphism, that you automatically get that all the higher brackets vanish. This is more difficult.
But it's not always true that like all the structures are the same. Right? There are multiple L-infinity structures.
Right, there are multiple ones, but there's an L-infinity isomorphism between them.
For any two random structures I choose.
They're both minimal models, yes.
Right. If they're both quasi-isomorphic, then yes.
Yeah.
Yeah. So maybe I just right. So actually, this example here works in some generality. So it's if A is AQ modulo I is a reduction system for the ideal, then there's a projective bimodule resolution of A from R. And you, sorry, yep.
What do you mean by Q?
Q is a finite quiver. Right, and so basically, if it's a quiver with one vertex and some arrows, then it's the free algebra in a finite number of variables, and otherwise you can have other path algebras of quivers with relations. And so there always exists such a reduction system, and then you can in the construction by Choi and Solitar, there also exists a bimodule resolution that uses this reduction system as input, and you can do this and obtain this right-hand side, this L-infinity algebra. Right, so this...
There is no D, right?
In general, there could be a D. Yeah. So if the resolution, for example, is not necessarily minimal, yeah. So in that example here, there's no D, but in general there could be a D. But still, you get a smaller complex that controls, actually naturally controls deformations of A, but it also controls naturally controls deformations of R, but it also controls deformations of A. So this gives an equivalence between deformations of A and deformations of R. And these deformations are sometimes more combinatorial and more easier to handle than those using this big DGLA. Yes.
Is the projective resolution the unique resolution?
This is the yeah, essentially the same idea. Yeah, but I don't think it's always exactly that one. So if the algebra is a monomial algebra, then this is the Bartel resolution, and the terms in the resolution come from Annick's work. You've seen that before. Yeah. Right. So basically, this is the first part I wrote about minimal models, and so here we saw one minimal model, and then even if it's not a minimal model, you could have a smaller complex controlling a deformation problem, which makes it easier to work with that. And then I want to also mention different construction. These are the higher derived brackets. And so, in a simple case, you could look at an algebra A, an algebra B, and an algebra homomorphism between them. And then ask A is in V and mu, so space V and a associative multiplication mu, and B is some other vector space, and associative multiplication on there. Then you can ask when is this data associative algebra homomorphism, where A tilde is now a formal deformation of A. So what that looks like, and B is a formal B tilde is a formal deformation of B. So it's this underlying vector space, and then deforming the multiplication there, and this is deforming the morphism. Right, and so what you can do is you look at following complex, which sort of looks familiar. So I want to define G as follows. So in degree n, I want to take this, which is sort of controlling, or the complex that controls deformations of A. And now I add color. I add things which takes inputs which are either V or W. And end up in W. So in particular, one is when all of them are W, and I get the term that I would expect to appear when I want to perform the multiplication on B. Then you can look at this subcomplex, and you see if n is 0, then I have a homomorphism from V to W, which corresponds to linear map here. So this is sort of what I will need to deform the morphism. And then actually here I have a bit too much, so I can look at the subvector space, and this is just the thing that I would need for the multiplications. And then the point is on this big one here, on G, there exists something like a Gassner-Haber bracket. It's essentially exactly the same Gassner-Haber bracket, just that you take care of what the inputs are and what the outputs are. And then the theorem by G which says that this diagram here, so this deformation star is diagram associative algebras, if and only if. Now, so what we have for associative algebras, we said in associative algebra sort of we have a formal deformation if and only if this U tilde is a Malpatin element, right? Opschild CGLA will be answered with the maximum idea. And now we want a similar statement. So for the first order terms, so the high order terms that I add on here, so this is the maximum. These are the things that I add on, and this is sort of what I need to see what conditions there are. This turns out to be, first of all, an element in this shifted complex. And so the statement of the theorem is to say that this is actually a diagram of associative algebras, meaning the formal deformations of the individual algebras are associative, and for those new associative structures, this new morphism is a morphism of algebras. And this graded vector space has an L-infinity algebra structure, which can be given by higher derived brackets. And these derived brackets are completely explicit. So now if I manage to write all of them. So I want to bracket two things which are here, or things from here and here, things that are only here. So maybe I write the mixed term. The terms are also explicit. So here you can see this is the bracket on the big CGV algebra here, and then phi is this bracket with the exponential of the bracket with phi, and then p is the projection from G to A, where this projection is given by this direct sum decomposition. So AN is a direct summand of this term here. And yeah, if you do that, you get completely explicit brackets. I didn't write down the formula for all of them. But this is another case where there's a natural VGLA for the one term here and for the other term. And if you want to combine those to look at simultaneous deformations, you get a natural L-infinity algebra structure.
Is the same structure as Magneti's mapping cone structure? Or
Yes.
A to G or G to A?
Actually, I think the mapping cone construction, basically you have A into G. Then there's like a homotopy fiber here. I'm not exactly sure. And there's a natural L-infinity algebra structure there. And the thing that's used here is that L-infinity algebra structure on this summand. And then you sort of have to add an extra summand and combine those. So it's closely related, but not exactly that. Yeah. So these explicit brackets are called higher derived brackets. And that's the construction by Bolonov. And they can be used for not just for associative algebras, but also other simultaneous deformation problems. So, you could take like two Lie algebras, L and L prime. Lie algebras, or something like co-isotropic manifolds of Poisson manifolds, or also generalized complex structures formed this way. And maybe I just finish by saying something more about diagrams. So deformations also deformations of the category of coherent sheaves on algebraic variety. X. And this is theorem by Lowen and Vandenberg, which says that there's an equivalence between deformations of abelian category of coherent sheaves and deformations of diagram that you get when you restrict the structure sheaf to an affine open cover, which is closed under intersections. So use an affine open cover. And just sort of relate this to the deformation quantization, the first order deformations up to equivalence. So this is the tangent space to the deformation functor. This is given by the Hochschild cohomology, second Hochschild cohomology of the variety or scheme. And when this is smooth, then you have a direct sum decomposition. And the first term there, these will correspond to algebraic Poisson structures. And the second term to classical algebraic deformations, or geometric deformations of X. Okay, I think I'm over time. I'll stop here.